Hi, I'm Antonio Sala, and in this video we are going to discuss a demonstration of linear matrix inequality problems, in particular finding the largest ellipse inside some convex body, intersection of a polygon and another ellipse. The meaning of largest will be subject to the condition that it must be amenable to convex optimization. So that will have some issues to be discussed. And in fact, if largest means the ellipse with largest area, then we will need some change to inverted form and additional stuff that will be discussed in a sequel video. In here we are just going to post the problem and present some preliminary linear matrix inequality constraints and cost index, but the largest area, which is the actual final solution we seek, will be discussed in that second video for brevity. So basically our goal is finding the largest ellipse inside this black boundary. So we'll end up with some shapes like this. So we'll first discuss how to pose the fact of being inside the black boundary as a linear matrix inequality constraint. And as we see, this shape is symmetric around the origin, in the sense that, well, if x is inside the required shape, then minus x is also inside it. There are more general versions of the things we are going to discuss, but as my ultimate goal is understanding linear matrix inequalities for control problems, in control our operating point is always 0 at the origin, and if we are considering linear systems or linear parameter varying systems, whatever, then things are symmetric around the origin. So I will not bother in introducing additional translation-like degrees of freedom in my problem statement. Then, how do we encode this shape? Well, a symmetric polyhedron can be encoded with some inequalities by stating that some linear functions, each row of ax being a matrix and x a candidate point to be inside our shape, then if row to row ax is between -1 and 1, then that can define a band, say x1 plus x2 between -1 and +1 would end up defining this band. And if I put many of them, then I get additional lines, whatever, defining a polygon. In this case, it's say that it's defined by faces, because we are writing the equations of the lines that conform the boundary. So the point that verify all inequalities will be those inside the polygon. So this is the way of defining a symmetric polytope. But well, if we square this, we can say x1 plus x2 squared less than 1, or the other stuff squared less than 1. So we can equivalently say then that this quadratic inequality also describes a polygon. In fact, these quadratic inequalities, if this is a generic positive definite matrix P, this will define an ellipse, but this P in particular is singular, is rank 1, so it defines an ellipse with an infinitely long axis around the center of the band. So we are changing linear inequalities by quadratic inequalities and saying that linear bands are just infinitely long ellipses in one direction. So we will use quadratic inequalities in X everywhere. So in here, for instance, we have 3 linear restrictions, 3 bands, 6 edges of the polygon, but we form this MI matrix and we will draw the bands with this implicit function showing the boundary of this. But well, once we enter the ellipsoid stuff, then we can just put some extra positive definite matrix in here that is not singular full rank, so it may define also just non-degenerate ellipse. Then, for instance, I can invent this M4 for a different ellipse and draw it as well. So we get this violet ellipse. This is the fragment of the boundary of this shape that has ellipsoidal curvature, and the other are the three linear constraints and the symmetric one from the linear inequalities or from the degenerate quadratic ones. Then, how do we define the interior of this black region? Well, if we have a set of constraints that must be less than 1, in particular quadratic ones in this case, if x must fulfill all of them, this means that what we are actually saying is that the maximum of everything must be less than 1. So defining a function of x being this maximum and plotting its boundary will define the black boundary, and that is what I did in MATLAB with the line of code I am putting here. I am plotting the boundary of the maximum of all 4 things that must be less than 1 to be in the required region I wish to explore. So with this, we have defined this black shape as the intersection of 4 ellipses, 3 degenerate ones and 1 standard non-degenerate ellipse. So once we have our restriction, then we need to find the largest ellipsoid, defining some optimization problem. My target ellipsoid will be this one, and P will be a decision variable, and I must make that ellipsoid, ellipse in this 2-dimensional case, large enough, the largest possible actually. So I need to find P, fulfilling some conditions, some linear matrix inequality conditions. First, note that the larger P is, the smaller the ellipsoid represented by this inequality is, in the sense that, okay, if I change P by 4P, then this is the same way of writing the same equation, but we see then that if P multiplies by 4, x divides by 2. So the size of P, the eigenvalues of P or something like that, is inversely proportional to the square of the size, just in vague terms, you know. But, okay, the thing is that once we realize that, if we wish this ellipsoid to be inside these bounds, it means that matrix P must be larger than matrices M1 to 4, formally understood as this fact that P minus each of the M's must be a positive definite matrix. We discussed that in other ellipsoid-related videos, but the thing is that, okay, YALMIP allows me just to insert this constraint like this. I start with an empty set of linear matrix inequality constraints, and then I add the 4 constraints. So with this fact, all positive definite matrices P, this SDP programming decision variable of size 2, then this line P is a symmetric matrix to be determined with some optimization, and then with this line I put the constraints that encode the fact that this thing must be inside the convex shape we were discussing a couple of minutes ago. So good, we have these constraints, and then which is the cost index? Well, the cost index needs to be something amenable to convex optimization, at least in principle, because non-convex stuff is much harder to optimize, takes longer, and we usually cannot guarantee that our optimization converges to a global minimum, so we'll stick to convex optimization, which is fast and has a single global minimum we are guaranteed to find to a given tolerance. So, for instance, one of the things we may optimize is saying that as this thing is the sphere of radius 1 over square root of this AA variable, then my ellipsoid being outside that circumference means that P must be smaller than AA times identity. So this is the circumference in this 2D case I am referring to, and I wish that the ellipsoid I'm searching for is outside that circumference, so I can encode that additional constraint, and then I can inflate the circumference by shrinking the value AA, and then the optimize command tries to find the minimum AA so that my conditions are feasible. So geometrically, that means that I am trying to inflate, and find the largest circumference so that an ellipse can be found in between it and the black boundary. So if I optimize it, well, I obtain something. The minimum AA is 13. If I inflate more, then, the circumference exits the black shape, and well, it obtains a P defining an ellipse that is larger than that circumference. So as you can see, the solution of the LMI solver is, well, the green ellipse, because once we have inflated the cyan circle, we have a lot of feasible solutions, let's say, which lie outside the circle. If we wish for the LMI solver to actually give me the P associated with the circle, well, it's the identity. But if we wish a unique solution, we can add this trick, because AA ends up being the maximum eigenvalue of P, and with this trick we try to minimize 0.9999 times the maximum eigenvalue, 0.0001 the minimum eigenvalue. So then we push not only on one of the axes but in the other one as well, but just with 10,000 times less intensity on wishing to minimize it. So if we repeat this, then MATLAB's output is the identity matrix, and then we have a unique solution. Of course, we may say, what happens if we just minimize the trace of P? Well, minimizing the trace is also a convex optimization problem. It minimizes the two eigenvalues of P with equal intensity, let's say, but as the eigenvalues of P are inversely proportional to the squared length of the axis, then we are making the ellipse large by minimizing this thing where sigma 1 and sigma 2 are the half axis lengths. And then, well, we get a large ellipse. Here we have it. If we plot it with F implicit, in green we have the circle solution to our first problem, and in cyan now we have the solution to the second problem. And well, this other ellipse is, well, large in the sense we defined of the trace, but of course then we are not pushing so hard the minimum radius, because if we see the radius of the largest circle inside my region is 0.2774, and as my effort in minimizing stuff is shared between both axes of the ellipse, then the obtained ellipse has a slightly suboptimal minimum radius with respect to our first version of this problem. But anyway, as this second problem of making the ellipse large by minimizing the trace is kind of strange, then we'll defer to a second video actually maximizing the area of the ellipse with some extra manipulations. For the moment being, we end here. In summary, in this video, we explained how linear matrix inequalities can be used as constraints to define the interior of the black shape, and then we solved the optimization problem of finding the largest circle inside the shape, the green one here, and we also thought on inflating an ellipse by minimizing the trace, which gave me the cyan ellipse, but that latter approach is kind of just an approximate way to maximize the area of the ellipse, which will be done in next video. So we finish here. Thanks for watching.